You're floating 4,067 miles above the moon, looking down at a world that no human being has ever seen this clearly before. There's no atmosphere blurring the view, no clouds, just silence, and a surface that looks like it's been shattered and reassembled 1,000 times over. You are farther from Earth than any human has been in 54 years. Most of us have grown up thinking we know the moon. It's the thing that hangs in the night sky. It's gray, it's cratered, it's dead. We've been staring at it for thousands of years. We walked on it more than half a century ago. How much could we possibly still have wrong? Turns out, quite a lot. In April of 2026, 4 astronauts aboard NASA's Orion spacecraft named Integrity flew around the moon for 7 hours. And what they saw forced scientists to completely rethink several assumptions we've held since the Apollo era. They photographed things that shouldn't look the way they look. They described terrain that didn't match our models. They captured a solar eclipse from a vantage point no human had ever occupied. And in the data coming back from that mission, geologists found something in the lunar crust that changes the timeline we've been using for billions of years. The moon is not what we thought it was. So what did Artemis II actually find? Here's how confidently we thought we understood the moon. After Apollo 17 landed in 1972, NASA had collected 842 pounds of lunar rock. Scientists spent the next 5 decades analyzing every gram. By the 2000s, the consensus was settled. The moon is geologically dead, mostly uniform in composition, and its far side is basically just more of the same, a heavily cratered, featureless wilderness. That's what 54 years of assumed knowledge looked like. Then, on April 6, 2026, humans actually went back and looked. Let's start with the far side, the side of the moon that always faces away from Earth, the side you have never seen with your own eyes. For the entirety of human history, it was invisible to us. Even the Apollo astronauts, who technically flew over it, couldn't study it closely because of the timing and angles of their orbital paths. NASA's Artemis II lunar science lead, Kelsey Young, described it as one of the most scientifically underexplored surfaces in the entire inner solar system. Here's the key. When the Artemis II crew photographed the far side at close range on April 6, 2026, what they saw didn't match the models. The far side is dominated by craters, far more than the near side, but scientists had never been able to explain why with high-resolution human observation. Now they can start to. The crew documented ancient lava flows frozen mid-pour, surface fractures running for hundreds of miles, and color patterns in the terrain that indicate mineral compositions no one had mapped at this resolution before. Lunar geologist James Day of the Scripps Institution of Oceanography said it directly. That human perspective is everything. The ability of trained observers to describe what they're seeing adds insight you simply can't get from images alone. But here's where it gets interesting. One of the most important targets was a structure called the Orientale Basin, a nearly 600-mile-wide scar left by a massive asteroid impact 3.8 billion years ago. We've known it existed. We've seen it from Earth, barely, at an oblique angle on the moon's extreme western limb. But from the Integrity, for the first time, the crew could see it in full cross-section. And what that revealed was something geologists had been hoping for since the Apollo era. Exposed rock from deep inside the lunar crust, pulled up by the force of that ancient impact and left sitting on the surface like a geological time capsule. Those rocks predate the moon's volcanic period. They are, potentially, among the oldest accessible material in the entire solar system. Now, some of you are thinking, we have orbiters, we have satellites. Haven't we already photographed all of this? Fair question. And the answer is no. Orbital imagery gives you data. Trained human eyes, looking in real time, making comparisons, adjusting for light and angle and color, give you interpretation. The crew noticed color differences across the terrain that indicated hematite, an iron oxide that, by rights, should not form easily on the moon without water. Hematite on Earth is what you get when iron rusts in the presence of oxygen and moisture. On the moon, that finding reopens a question scientists thought was settled. During the flyby, the 4 crew members worked in shifts. Pilot Victor Glover was asked to compare the topography of the moon's north and south poles, something no human had ever done from this vantage point in real time. He described seeing quite a bit of elevation change across the South Pole and noticeably smoother terrain toward the north. That single observation has real stakes. NASA's next mission, Artemis III, is targeting a landing site near the South Pole, a region so rugged and shadowed that entire craters haven't seen sunlight in billions of years. Inside those permanently shadowed craters is thought to be something extraordinary: water ice. Here's the part that gets me. The South Pole isn't just a dramatic landing backdrop for a future mission. If the ice is there, and the data increasingly suggests it is, it represents the single most valuable resource in the history of space exploration. Water ice can be split into hydrogen and oxygen. Hydrogen fuels rockets. Oxygen keeps humans alive. In short, the moon's South Pole may be a fueling station for the entire solar system, sitting there, frozen and waiting, for 3 billion years. Glover's topographic comparisons from Integrity are now informing exactly where Artemis III will attempt to touch down in 2028. The crew also captured something that had never been photographed by human hands from this position: an Earth set. Earth, dropping below the curved limb of the moon. Then, minutes later, an Earthrise. Echoing the iconic Apollo 8 photograph from 1968, but from an angle slightly farther out, slightly more revealing. And in between, a solar eclipse, the moon passing between the spacecraft and the sun, exposing the corona in a way that made the sky around it look like it was on fire. Then, the crew came home. On April 10, 2026, the Orion spacecraft Integrity splashed down off the coast of San Diego. The astronauts were recovered. The data was secured. And the engineers started doing something nobody had expected to go this smoothly. Everything worked. After Artemis I in 2022, the Orion heat shield had experienced unexpected erosion, chunks of the ablative material burning off during re-entry in ways the models didn't predict. It was serious enough to delay Artemis II for more than a year. Engineers redesigned, recalculated, and held their breath. On April 10th, the heat shield performed better than projected. Not just adequately, better. Here's what that means. We had built a model of how the moon's orbital return trajectory works under real crude conditions. The model was wrong, and we corrected it not with simulations, but by going back and doing it. This is the part of the Artemis II story that doesn't make headlines but should. Because every assumption we've carried forward from Apollo was made 50 years ago, with 1970s computers and incomplete data. What Artemis II proved is that returning to the moon forces you to update every single one of those assumptions. And some of them, the ones about the heat shield, about the far side geology, about the South Pole topography, about hematite and water, turned out to be meaningfully, importantly wrong. The corrections are compounding now. Artemis III is targeting 2028. It will use the topography data from Glover's observations to select a South Pole landing site. The Aximu spacesuit, a new generation of lunar hardware, will undergo in-space testing aboard the International Space Station in 2027. A National Academy study is currently underway to identify the highest value landing zones based on what the Artemis II crew documented. More missions means more data. More data means more corrections. More corrections means we're finally building an accurate picture of a world that we stared at for thousands of years and thought we understood. Scientists will be analyzing Artemis II mission data for years. The Avatar organ chip experiments that flew aboard Integrity are being compared to ground controls using single-cell RNA sequencing. Information that will eventually let NASA send personalized medical kits ahead to the moon for future crews. The CubeSats deployed from the mission are mapping radiation environments in deep space that no instrument has measured this precisely. Every layer is revealing something we got wrong. You've looked at the moon your entire life. You grew up thinking humans had already done the hard work of understanding it, that the Apollo missions wrapped it up, filed it away, and left us with a tidy answer. But the moon was never a solved problem. It was a paused one. For 54 years, we stopped going back. We stopped looking. We filled in the gaps with models and assumptions and called it knowledge. And then 4 people climbed into a spacecraft called Integrity, flew 694,000 miles, and looked with their own eyes, and the gaps opened right back up. The Oriental Basin is exposing rocks from the birth of the solar system. The South Pole may hold the fuel for humanity's entire spacefaring future. The far side has been sitting there, misunderstood, for as long as we've been watching the sky. We didn't know the moon. We just thought we did, because looking up felt like the same thing as understanding.